This lesson is the second half of Module 12 on geometric optics. And so we're going to start. So far we've looked at what happens to light when a beam of light hits a reflective surface like a mirror, and we've looked at convex and concave mirrors and what happens to light in those instances. Now we're going to look at what happens when light hits a transparent object. So when light hits a transparent object like glass, so if I have a piece of glass and light is traveling in air, it'll hit that glass. Why is it doing this? It'll hit that glass, and then part of it will get reflected, like we saw with when it hits an opaque surface. And the law of reflection will tell us that this angle will be equal to that. Actually, it's different. Let's see. This angle will be equal to that angle for the reflected beam. But then another part of the light will actually bend a little bit. And so the light beam will bend as it goes through the transparent surface. So a part of it gets reflected, but then a portion of the light that travels through the transparent surface will bend. And so this angle will be smaller than the angle of incidence. And this part of the beam that bends, we say that it is refracted. Okay, so then we ask the question, why does this happen? And is there a way that we can calculate what the refracted angle will be? Okay, so if you want to look in your book at figure 12.8, this is on page 491. So when a beam of light hits, when a light beam comes in, so let's say we'll just say this is glass, it could be water or some other substance that light can move through. But when the beam of light comes in and it's going to hit that surface, because it's hitting at an angle, then if we look at the crest of the wave, one portion of that crest is going to it's going to enter the glass first, and then when it does, it's going to slow down. And yet, remember that frequency is equal to velocity divided by wavelength. So one part of this is going to enter the glass before the other, and so it's going to slow down. So if velocity decreases, and yet the frequency of the light's not going to change, and therefore the wavelength has to decrease in order to keep the frequency the same. And so the only way that you can decrease the frequency of the wavelength, and keep the frequency the same is that you have to keep, so the wavelength of these is going to increase. The wavelength is going to decrease because the velocity decreases, and yet these crests of these waves still have to line up. So the only way that can happen is for this beam of light to bend. So that explains why it happens. Why is it that a beam of light, when it hits a transparent surface, will bend? So a man by the name of Snell, and this was actually in the 1600s, around the same time as the Pilgrims, he studied this phenomena and he came up with Snell's law. And Snell's law states that N1 times the sine of angle 1 equals N2 times the sine of angle 2. Okay, so angle 1 would be the angle of incidence, and then angle 2 would be the refracted angle. Okay, so as that light is coming in, and this would be angle 1 right here, and then angle 2 would be the angle of the beam of light that is refracted. Okay, so then what is n equal to? Well, n is the index of refraction. And the index of refraction depends on the medium that the light is going to be traveling through. So n is equal to it's equal to c over v. And c is the speed of light in a vacuum divided by the speed of light in the medium that we are interested in. Okay, so the first thing you need to know, so you know that we have said that the speed of light was 3.0 times 10 to the 8 meters per second. Well, that's the speed of light in that's the speed of light in a vacuum, and the speed of light in a vacuum and the speed of light in air are so close, so we just assume that they are the same, and therefore, if we assume this is the same, so this is in the vacuum, this is in air, then n for air is going to be equal to 1.00. Okay, but then the speed of light slows down when you go into more dense substances. So if n is equal to c divided by v, if it's a diamond, so a diamond is more dense, so you're going to, that means the speed of light is going to be decreasing, and so n is actually equal to, I think it's 2.42. For ice, n is equal to about 1.31. Okay, so this would be 3.0 times 10 to the 8th meters per second, and then divided by some smaller speed, so that if you divide by a smaller number, then your n is going to be larger. So the more dense the substance, the slower the speed of light through it. Okay, so then, if we know the substance, then we can determine the angle of that refracted beam. Okay, so let's start by just doing on your own 12.4. And for this one, so let's remember that N is equal to C divided by V. So this problem says the index of refraction of water is 1.3. What is the speed of light in water? Okay, so we are told that N is equal to 1.3. And then we want to know what is the velocity of light in water. Okay, so we are going to solve for V. So we're going to multiply both sides by V. That gets rid of this over here and divide both sides by N. So V is equal to C divided by N. Okay, so remember C is the speed of light in air. So that's going to be 3.0 times 10 to the 8 meters per second. And then N we were given as 1.3. It has no units, so will be the units that will be left with will be meters per second. So the velocity in water will be equal to comes out with the numbers. We can have two significant figures, so it comes out to 2.3 times 10 to the 8 meters per second. Okay, so the speed of light in water will be 2.3 times 10 to the 8 meters per second. Okay, then let's look at 12.5 on your own 12.5. Okay, so this says a light wave travels through air and then it encounters diamond. Okay, so it's the light wave, this is diamond. So that light wave is going to travel through air and then it's going to encounter diamond, and we want to know, and it's going to bend. So it's going to bend somewhat. And we want to know what is the angle that it will bend. Okay, so what we are told is that N for diamond is 2.42. So this is for diamond. We know that N for air is equal to 1.00. And then we are told that the angle of incidence, so that would be angle 1, is 67. That's 67.1 degrees. Okay, so Snell's law tells us that N1 times the sine of angle 1 equals N2 times the sine of angle 2. So we want to know what is the angle of the refracted beam. Okay, so we'll just divide both sides by N2. Okay, so that gets rid of that. So then we just plug in our numbers. So 1.0 times the sine of 67.1 degrees divided by N2, which is 2.42, that will equal the sine of angle 2. And I get 0.381 equals the sine of angle 2. So then if you hit on your calculator, if you do the shift sign or inverse sign, then the angle comes out to be 22.4 degrees. Okay, so that light will go in at an angle of 67, and then it will bend when it goes into the diamond, and that angle now will be 22.4 degrees. So that entering the angle of incidence is 67. The angle of refraction is 22.4. Okay, so that is on your own 12.5. And then lastly, we will do on your own 12.6. Okay, so this one tells us that a light ray travels through glass and then encounters air. Okay, so it's going into glass first, so that means N1 would be equal to 1.5, and the angle 1 is going to be 34.6. And then we know that then it's going to go into air. We know that air is 1.00, and then we want to know what is angle 2. Okay, so it would be 1.5 times the sine of 34.6 divided by 1.00 will give us the sine of angle 2. So this will come out to 0.85 equals the sine of angle 2. And so angle 2 will be equal to 58.4 degrees. Okay, so it will be traveling slower in the glass, and then it will speed up when it gets into the air, and therefore the angle will be greater in air compared to glass. Okay, so that's the application of Snell's law. There's some of those in the back of your book, or in the back of the module, that you can work on as well. Okay, so then the next thing we need to do is what happens when light travels into a lens. So we know that when light travels through transparent objects, it tends to bend. So what happens when it travels through a lens? So first of all, when we do lenses, we're gonna draw these lenses as if they're thick, because it's easier for us to picture what is happening. But keep in mind that lenses are very thin. And also keep in mind that light can travel through both ways in a lens, right? So the light could travel this way, but it could also travel that way. And so there will be two focal points. There'll be one on each side of the lens, because the light can travel both directions. And when we're measuring the focal point, we measure from the middle of the lens. Okay, so if we're told the focal point is 5 centimeters, we would measure that from the middle of the lens in both directions. Okay, so lenses are thin. There's a focal point on both sides, and we measure the focal point from the center of the lens. Okay, so there's two types of lenses. The first type of lens is called a converging lens. And it's called a converging lens because any light beam that travels horizontally through it will pass through the focal point. So in other words, all of the light beams traveling into a converging lens will converge or come together at the focal point. So if we have a lens like this, and here's we'll go ahead and draw our line through here. Here's our focal point. So in a lens like this, any light beam that travels horizontally through this lens is going to travel through the focal point. Kind of missed it there, but okay, so anything horizontal is going to converge on the focal point. Horizontal is going to converge at the focal point. Horizontal is going to converge at the focal point. Okay, so that's what a converging lens is. Any beam of light that travels through that lens horizontally is going to bend and converge at the focal point. So we, just like we have done before, we can predict what an object will look like when it is viewed through a converging lens. Okay, so two rules. There's actually three rules, but we're just going to apply two of them. So if they enter horizontally, we just said the light rays that enter horizontally will exit through the focal point. I'm not the one that's doing that. And then secondly, if any light beams that enter through the focal point will exit horizontally. Okay, so those are just the opposite. If it enters horizontally, it's going to exit through the focal point. If it enters through the focal point, it will exit horizontally. Okay, so and those are the same two things that we saw when we looked at mirrors. The same two rules. And then also you could also say that any ray that travels right through the center it won't be deflected. It'll travel straight through the center. So we just won't even worry about that one. Okay, so let's do example 12.5. We'll go through this together, and then we'll do we'll do some of the on your own. Okay, so let's draw our lens. And remember, everything's going to be measured from the center. It's really hard for me to do on this screen. But we're going to measure everything from the center. So I'll try to go down through the center of this lens that way, and then through the lens that way. Okay, so an object is 10 centimeters from a converging lens that has 7 centimeter focal points. Okay, so let's draw our focal points first. So we'll say that's 7, and there's going to be a focal point on both sides, same distance, 7. And then it says that our object, so if that's 7, we'll say this is 10. So our object is 10 centimeters from, and we're measuring this from the center of the lens. So we're measuring this, that's 7, that's 7, that's 10. Okay, so what would this object look like? So let's draw our 2 lines. We'll start with a red one. So our first rule is that so we're going to start at the top of the object, and it's going to travel in until it hits the center of the lens, and then it is going to exit through the focal point. Okay? And then the second one says that and we'll draw this one in blue, if it goes through the focal point, so it's going to go through the focal point until it hits the center of the lens, and then it will exit horizontally. Okay, and we can see then that our blue and red lines, the light that the exiting lines are going to meet right there. Okay, so remember, just like before, this is the bottom. So this is the bottom. So if that's the bottom and this is where it's meeting, so it's going to be inverted. And what about its size? So here is how big it was, and now it's going to go from there to there. So it's going to be magnified. This is bigger than this. It's going to be magnified. And because the lines intersected without needing to be extrapolated, then we would say it is a real image. And when we say that it is a real image, that means that it will look to the observer. When you look through this lens, it will look to the observer as if the object is on the other side. So as you look at the object through this lens, it will appear to be on this side. Okay, so that is the first example. Let's do a couple more of those just to get some more practice. Let's do 12.7. Okay, so again, let's draw our lens. And we'll draw it thick, even though we know our lens is really thin. Draw our line through the middle, and then our axis through the middle. And this tells us that focal points are 5 centimeters. So again, those focal points are going to be measured from here. So we'll say that's a focal point there. And from here, we'll say it's there. Okay, so there's our 2 focal points. And then it says that the object is 10 centimeters from the lens. So it's going to be twice this distance. So here, we could go here and then double that. So here is our object. Okay, so let's draw that object like that. Okay, so then what will happen? Okay, so we know that we'll go red first. So it's going to go in horizontally until it reaches the center of the lens. and then it's going to exit through the focal point. And then the other one is going to go in through the focal point until it hits the center of the lens, and then it's going to exit horizontally. So these two will intersect right there. Okay, this is the bottom, so this is the top. So our object is going to be like this. So it's upside down, so it's inverted. It's real. You didn't have to extrapolate. So when you look through the lens at this object, it's going to appear as if it is on this side. And then it looks like it's about the same size. Okay, so this is about the same as that. Okay, so that's 12.7. Let's go ahead and do 12.8. So 12.8, again, we'll draw our lens here, draw our line down through the middle, and like this. And now we said that the focal points are 8 centimeters. So from the middle, this will be 8. So we'll try to make that about the same distance. Okay, so those are our 2 focal points there. So there's our focal point, and there's our focal point, and now the object is 5 centimeters from the lens. Okay, so here's our object. So then what's going to happen with this one? Okay, so the first thing we would say is, let's go red first. So we're going to go in horizontally, and then it's going to go out through the focal point. And then the second one, since the object is in front of the focal point, it can't go through the focal point, but we can extrapolate this out, and so it looks like it's coming from the focal point, and it will do that until it hits. I should have made that one blue, sorry. But we can keep these separate. Now let's go blue. Okay, so it can't go through the focal point, but it'll come from the focal point. So we'll go until it hits the center of the lens, and then it will exit horizontally. Okay, and those two do not intersect with each other, right? So what we have to do then is we have to extrapolate them out. So here's our blue one that exited, and our red one exited this way. It came in horizontally and exited. So then we will extrapolate the path of exit here. Okay, so those two will intersect right there. Okay, so here's the bottom. So this is the top, so it would be like this. So we would say that it is upright. And it is enlarged or magnified. So this is bigger than this. And then lastly, we would say that it is a virtual image. because it was formed by lines that had to be extrapolated. And so now in this case now, a virtual image, the object will appear as if it's on the same side as the object was when we looked at it. Okay, when we looked through it, as the same side that what we see will appear to be on the same side as the object actually is on. Okay, so that is on your own 12.08, and that is, those are converging lenses. Okay, then there is another type of lens that is called a diverging lens. And what a diverging lens does, so they're shaped differently. They're shaped more like this. And what happens with a diverging lens is that any light beam that travels in horizontally, then it bends away. They bend away from the center of the lens. So one coming in here would bend out like that. One that would come straight in would go like that. If it comes in here, it's going to bend out like that. Coming in here, it's going to bend out like that. Okay, so because of the way the curves are, any horizontal light beam, they'll bend away from each other when they enter the lens. And just like with the converging lenses, we can estimate we can predict what an object will look like when it travels through a diverging lens. Okay, so let's go ahead and draw our lens. And again, everything is measured, a really straight crooked line, but everything is measured from the center of the lens. So we'll go ahead and draw our line down the center, and we'll draw one through the center here. Okay, so example 12.6 says that the focal points are 5 centimeters. So this is 5, that's a focal point, and again it's a lens, so there'll be focal points on both sides. And then it says that the object is 7 centimeters away. Okay, so we will draw that object right there. Okay, so the same two rules. If it goes in horizontally, it will exit through the focal point. And if it goes in through the focal point, it will exit horizontally. Okay, so now these are a little more tricky, so follow me and then if it goes in, I'll do the first one red, it's going to go in horizontally, and when it reaches the center, it's going to exit through the focal point. But remember, the light rays are going to move away from each other. So when we say it exits through the focal point, it's through this focal point. So we would extrapolate this out, and so it will exit out okay, so in horizontally, and then it would exit out as if it were coming from this focal point down here. Okay, and then the other one would go in as if it were going through this focal point. So we're going to draw that line toward that focal point, and then it is going to exit horizontally. Okay, so there's our two lines, and as you can see, they didn't intersect with each other. So what we have to do then is we have to extrapolate the ones that the exiting lines. So this red one, this was the exit line, so we're going to extrapolate that out. And then the blue one, it exited horizontally, so we'll extrapolate that like that. And so those two are going to intersect with each other right there. Okay, so this is the bottom, so this is the top. So we would say it's upright. And if we compare this to this, we would say it's reduced. And because we had to extrapolate the lines, we would say that it is virtual. Okay, so the diverging lens is different because the beams of light will bend away from, they'll bend as if they came from the focal point on the same side of the lens as the object. Okay, so let's do a couple on your own. Let's do on your own 12.9. Okay, so we'll draw our diverging lens. And we'll draw our line through the middle there, and our line through the middle there. Okay, and the 12.9 says that the focal points are 7 centimeters. Okay, so again, we're measuring from the middle, so we'll put a focal point there, and then about the same distance here, we'll put a focal point. And then it says that the object is 16 centimeters away. So if that's 7, we're going to at least double that, a little bit more than double that. So we'll put our line right there. Okay, so let's go ahead and look at our 2 lines then. So the first one will go in horizontally. We'll draw it in horizontally till it reaches the center, and then it's going to diverge as if it came through this focal point. So it'll go out like that. And then the next one will go in as if it were going to go through the focal point. But it will, and then it will diverge horizontally. Okay, so it's going to be heading, the blue one will be heading toward the focal point. So it's going to go from here as if it's going to go toward that focal point, but then it's going to exit horizontally. Okay, and as we can see, they do not intersect with each other, so we will need to extrapolate those lines. So let's see, we'll extrapolate the red one. So it would be here, and we'll extrapolate that blue one straight out here. So they're going to intersect right here. I'm going to make that black. They'll intersect right there. Okay, so this is the bottom, so that's the top, so it'll be like that. So we would say it's upright. It is reduced. And because we had to extrapolate the lines, it is virtual. Okay, so that is the on your own 12.9. And again, there are some of those in the back of the chapter. I will record all the solutions on a separate video so you can see those worked. So I guess we can go ahead and do on your own 12.10. Okay, so in this one, it's a diverging lens. Okay, so here's our lens. Draw a line down through the middle, like this, and the focal points are 8 centimeters away. So we'll put the focal point there, and the focal point there. And then the object is 5 centimeters away. Okay, so we'll put the object right here. Okay, so what is going to happen in this case for 12.10? The first one will go in. So it's going to go in as if it came through the focal point. So right here, and it's going to diverge. Let's erase that one. Do the other one first. Let's start over here. Okay, so there's our focal point. Let's move that one back a little bit. Okay, so the focal points were 8. So there's F, and here is F, and then our object is 5. Okay, so first one will go in horizontally, and then it will diverge as if it came through this focal point. So it's going to go out like that. The next one will go in as if it were going to go through that focal point. Oh, change my color. So it's the blue one will go in as if it's going to go through that focal point, and then it's going to exit horizontally. Okay, so we can see they do not intersect with each other, so we'll have to extrapolate the blue one out here, and we will need to extrapolate the red one out here. So they will intersect right here. Oh, I'm sorry, where they intersect? They will intersect right here. Okay, so that's the bottom. And so this is the, well, let's see. I guess I drew that a little bit crooked. It'll be upright. So the line, they should have intersected a little bit above here. So it'll be upright. It will be reduced, and it will be a virtual image. Okay, so that is all. Those are the on your owns relating to divergent lenses. I want to say just a few things about the human eye. So as you know, your eye has a lens in it, and the type of lens that it has is a converging lens. And the reason it is a converging lens is because all of the light that enters the eye needs to be focused on one area in the back of the eye that is called the retina. So any light that's coming in here needs to be focused on the back of the eye. So as light enters, goes through the cornea, it goes through the pupil, then it hits the lens, and then all of the light needs to converge onto an area back in the back of the eye that's called the retina. Okay, so it's a converging lens because of that. Well, what you should have realized from all of the problems, all the ray tracings that we did, is that where the image appears to come from depends on where it was relative to the lens. So as the object moved, as we moved the object, that determined where the image was formed. Well, in what happens in a human eye, you don't have a situation where you can focus the image in different places because it always has to be focused on the retina. So the wonderful thing about the human eye is that the shape of the lens can actually change so that the light coming into the eye always focuses on the retina. So there are muscles, the ciliary muscles that attach to the lens, and they can relax and make the lens fatter like this, or they can contract and they can stretch out the lens so that the light that is coming in can always be focused on the retina. So the focal point of a lens changes depending on what the object is and where the object is located. Now you may know that, you probably know, some of you I'm sure wear glasses, so not all of our lenses work perfectly. So there are two conditions. One is called myopia. This is called nearsightedness. Most people who wear glasses are nearsighted. And then hyperopia is farsighted. So these people can see things close up, but they can't see far away. So I'm nearsighted. Farsighted, you can see far away, but you can't see up close. So our lenses don't always work perfectly. And what happens in nearsightedness is that the focus is, the light gets focused too strongly. So instead of the image forming on the retina, so if you have the lens here and the retina over here, instead of the image forming on the retina, it actually forms in front of the retina with nearsightedness. And so what we do to correct that is we use a diverging lens. So you can wear a pair of glasses or contact lenses that is a diverging lens, and then what that does is that you basically unfocus the light a little bit so that it's not focusing quite so sharply, and it'll focus on the retina instead of in front of it. For farsightedness, the opposite happens. So in farsightedness, here's the lens, and that's a really bad lens. So here's the lens, and the retina is back here in the back of the eye. What happens with farsightedness or hyperopia is that the light doesn't get focused strongly enough. So in other words, it doesn't get bent strongly enough. And so the image, instead of getting focused on the retina, it gets focused behind the retina. So if you're looking at somebody, at a person, it would be focused, it would actually, all the light rays coming from that person would focus behind the retina instead of right on it. And so then we need it to focus more sharply. And so then we would use a converging lens to focus those light beams more sharply so that they would go right onto the retina instead of behind it. So for farsightedness, your glasses that are used to correct it are converging lens. For nearsightedness, the lens that is used to correct it is a diverging lens. Okay, so we will stop there. That's it for Module 12. I will, in a separate video, I will record the solutions to the practice problems for Module 12.